In this section, we're going to establish an important sum concerning logarithm. To this end, we're going to first prove the following lemma, which states that if you look at the summation of the hth power of log of x divided by n for n less than or equal to x, the growth rate of this is a big O of x. Here h is a positive number. And now let's prove this. First, let us separate the left-hand side into two parts. We'll single out the term when n is equal to 1. And we take the sum of the rest. And now, we'll get the upper bound of this guy by an integral. We keep the first term, and for the second term, for each individual summand, we see that it is upper bounded by log of x divided by t to the hth power. This is an integration from n minus 1 to n dt. And this inequality follows from the monotonicity of log of x divided by t to the hth power. This integrand is monotonically decreasing when t increases. This is because log of x divided by n to the hth power is less than or equal to log of x divided by t to the hth power for t in the interval from n minus 1 to n. And now we can put together these integrals. This will be the integral from 1 to x. And now you see why we have to single out this first term. Because if you don't single it out, this t will start from 0, which is the singularity of this function. Now, in order to give this guy an estimate, we're going to perform a U substitute, as in the first year calculus. With a U equal to x divided by t. Now, when t goes from 1 to x, U will go from x to 1. And by chain rule, the additional factor here will be negative x divided by u squared. Now we simplify this. And we'll majorize this integral to the integral from 1 to infinity. And now, observe that this integral is convergent. This is a finite integral because logarithm grows slower than any positive power of monomial. So this guy will be bounded by 1 over u to some delta with delta bigger than 1. So by the p-test, you will see that this integral is finite. Yeah, this is from the calculus. And we factor out this x. And for the same reason, you can see this guy grows slower than any positive power of x. So they together will be a big O of x. And with this, we finish the proof of this lemma, namely theorem 423. With this lemma in hand, we prove the following estimate on the summation of lambda of n divided by n for n less than or equal to x. We'll show that this guy is log of x plus big O of 1, namely a remainder bounded by a constant. And recall, lambda of n is equal to log of p if n is the power of p. Otherwise, it is 0. I'll write down the definition of it when we use it. To prove this, we first put h equal to 1 in the previous theorem, and it follows that log of x divided n for n less than or equal to x is equal to big O of x. This theorem actually tells you the growth rate of the sum is always x, independent of the choice of h. And this h might only affect the constant in front of this x. And now we rewrite this sum. We can pull out this log of x out, and the rest will just be the summation for all n less than or equal to x of 1s. So you get the floor of x times log of x. And now, if you move the sum of log of n's to one side, you'll see it grows like x times log of x plus big O of x. Now we make the following claim. To set up a bridge between the sum and lambda of n, we'll show that sum is equal to the summation for n less than or equal to x of the floor of x over n times lambda of n. And at this point, let me recall the definition for lambda of n. To prove this, we're going to first collapse the sum into a product. And for this factorial, again, we're going to use the rounders formula for the prime factorization of factorials. And now observe that we can drop this floor notation. And now let me explain this. If you look at the Euclidean division for the floor of x, it is equal to p to the m times q plus r, with q equal to precisely this floor and r between 0 and p to the m. Now we're going to add x minus floor of x to both sides. What do we get? We'll get x equal to, now the remainder becomes r plus x minus floor of x. But these three terms together is still less than p to the m, because x minus floor of x is always strictly less than 1. Therefore, the floor of x divided by p to the m is still equal to Q, which is same as the floor of this guy. And this verifies these two things are equal. And now let's continue. We'll break this product again into the sum. And now, as a last step, we make the following important observation. We claim that this sum is precisely the sum we want. The summation over all n of the floor of x over n times lambda of n. Why is this true? This is true simply because of the definition of lambda of n. I said there's nothing other than just the definition. Look, lambda of n is equal to log of p if n is equal to p to the m. And now otherwise, it is 0. Although it looks like this sum has more terms than this sum. But by definition of lambda, you will see the actual terms are all equal to 0, because whenever n is not a power of p, the individual summand will become 0. And this verifies our claim. Now, to finish the proof of theorem 424, it suffices to connect the right-hand side of this claim to the left-hand side of theorem 424. So now let's rewrite the right-hand side by dropping this floor notation. I will call this part E, and E stands for error here. To give a bound for E, we observe that the coefficients are bounded by 1, so this is less than or equal to the summation of lambda of n's is n less than or equal to x. And the sum is precisely equal to percent of x by definition of percent of x. So this is nothing but definition. And percent of x, we know it is a big O of x by theorem 414. We proved. And thus, if you move this E to the left-hand side, and using this estimate, you'll see, and from what we derived above, the summation of log of n for n less than or equal to x is equal to what? Is equal to x times log of x plus big O of x. And that big O of x here will merge with this big O of x. So this is equal to x times log of x plus big O of x. And now we divide both sides by x. This yields the result we need for theorem 424. So we are done with the proof. Now, as a corollary to theorem 424, let's prove the following. We'll show the summation for all prime p less than or equal to x of log of p divided by p is also log of x plus something bounded by a constant. To prove this, we're going to look at the difference between and now we'll rewrite the first sum in terms of log of p. Remember, we did this before. This is nothing but the definition for lambda of n, because lambda of n is log of p if n is a power of p. Otherwise, it's 0. So they are equal. And now, what is the difference between these two things? You should be able to see immediately that this sum is precisely the situation when m is equal to 1. So the subtraction of this is just the summation of this guy, this sum, when m starts from 2 instead of 1. And now we're going to give an upper bound of this by dropping this x. Namely, we're going to sum up all possibilities. By Fubini's theorem, we switch the sum, and this is just going to be a summation for all p's of this geometric series times log of p. By using the formula for the sum of geometric series, this is 1 over p squared divided by 1 minus 1 over p. And from calculus, you can easily see this is a. Therefore, the difference between these two guys is still bounded by a constant. And this difference is also a positive number. This proves theorem 425.